toward M theory, brains, and then the Calabi-Yau spaces that just came up again, one of the more unintuitive but thrilling aspects of string theory is that it requires more than the three macroscopic spatial dimensions we're all familiar with in everyday life and that fourth temporal dimension. But why does it require more dimensions, and how do you visualize them? How many are there? And again, I imagine that, or I suspect that for at least a brief period, we can leave M theory and the potential of 11 dimensions aside, unless you think it's a worthwhile complication to bring in now.
Interestingly, I think that question only has a technical answer.
Okay.
You ask the question, can I, string theory is a set of rules. One of the ways that modern physical theories are formulated is there are many kinds of questions you could ask. But one question you could ask is, if I throw an electron and a proton at each other and they interact, what comes out? That's a question the laws of physics are supposed to answer. And in fact, it's widely believed that if you knew the answers to all such questions, like any set of incoming particles, throw them at each other at different velocities and so on, what will come out? It's widely believed, that's the so-called scattering problem, that if you know the answer to every scattering problem, you know everything. That's one way of writing down all the information. And that's how much, that point of view sort of started getting a foothold sort of in the 40s maybe, or 30s even. And so you can ask, but if you want to talk about gravity, you have to include in the list of things you scatter gravitons, which are the particles of gravity. And so if you could give the rules for scattering amplitudes involving gravitons, in some sense, you know everything if you give those rules. And so string theory was an algorithm for solving the scattering problem for anything, including gravitons. And you could not get self-consistent answers without either directly being in 10 dimensions or secretly being in 10 dimensions where you curl up some of them. It's a technical answer. But it's interesting. Self-consistency drives us to it.
No, that's good. Because I was going to ask, why string theory as it currently exists makes extra dimensions necessary, or alternatively, why would it be useless to search for versions of string theory without these extra dimensions to preserve our spatial intuitions? But you've already given the answer, which is that consistency is the constraint, and that's why they're necessary.
And so that's good, right? Consistency is a good thing. We'd really like more of it. What people were so high with how far we got with consistency that some people, that there was a kind of hope that started in the mid 80s that I don't think really. It sort of lingered on to around 2000, and somehow, if we understood all the consistency constraints, that there would just be one theory that made sense. I I don't think many people are pursuing that idea anymore, but it was something that was on the table. Of course, that would have been amazing if it were true. But doesn't seem to be true.
One dimension, no. Well, I guess I have to say the pun was intended, as I chose that word. Is of the question as I initially put it that I don't think you answered is how you visualize or because you do a lot of work visualizing, like with the Calabi-Yau spaces, visualizing these things. So how do you visualize the additional 6 dimensions, and are they, maybe this is a good place to start, are they also analogous to one another in the same way that our 3 macroscopic spatial dimensions are somewhat analogous to one another?
Yeah, they are. I do a lot of visualizing, but visualizing has its limitations, and ultimately what falls back to the equations, which the equations can have much more information in them than any pictorial image that we can carry in our minds.
But so what do the curled up dimensions, how small are they? How can they be envisioned for people who haven't encountered the idea before?
Well, the natural size for them, and there's kind of 2 ways you could ask the question. If you just kind of say what would you generically expect? You'd expect that the size of the extra dimensions is 10 to the minus 33 centimeters, which is a billionth of a billionth of a billionth of it. It's tiny, right? That would be the natural size. Then there's a very interesting question of, okay, but could it logically be bigger? And what is the actual experimental? Forget about what's natural. What does, after all, there are lots of things in our universe which aren't natural. We started out discussing that. The size of the cosmological constant, the Higgs mass. So maybe the dimensions are much bigger than you would naively expect, just using Occam's razor. And you can ask the question, how big could they be without having a conflict with experiment? We know that they're not a meter across because then we just see them. We could look in 4 different directions instead of 3. And in one of them, if it were small, if it was a circle, we'd see the back of our head, that doesn't happen. So they're not a meter, but how big could they be? Well, surprisingly big. So my Arkani Ahmed Diwali at Demopolis showed a long time ago. I think that was late 90s, maybe. When was that paper? And also Lisa Randall took another, and Robin Sundrum took another kind of take on this. That surprisingly, the experiments allow them to be big, so big that it's not impossible we could see them experimentally. Now, it could happen. It could happen that and there have been experiments done which put more and more stringent bounds. It's been, over the years, it's been shrinking the experimental upper bounds on how big the dimensions could actually be. And I don't think they're going to, it's important to continue these experiments because we have to do everything we can. And these are really great experimentalists who are doing this. But I'm not betting that they'll see them. I think extra dimensions could be there. They're a logical possibility, but there's no good reason they would want to be so big.
I know that we're talking about dimensions right now, and not strings or brains of other dimensions. But you mentioned this idea of you could look and see the back of your hand, and for whatever reason that brings to my mind, and since we were talking about the possibility of observing strings, that I don't know if Witten, who is my understanding, because I'm not really in this field, he's the physics genius of our age, has suggested that it's a possibility that there could be strings out there that are large enough on a cosmic scale that we could observe them through a telescope, because the levels of energy at the Big Bang could have produced them. So that's a possibility.
It's a possibility, right? And indeed, there was an exciting moment. There was an exciting moment when astronomers thought they'd seen something like that.
Oh, really?
From lensing of stars. That was after Witten's paper, I think. And that's that could have happened. It's not logically precluded. They could have measured the extra dimensions. They could have seen strings stretching across the sky. All those are logical possibilities. It's not precluded. And I think it's a sort of logically important aspect of the theory that you could get evidence for it. It's, there's some theories that, they don't make any predictions. They're interpretations. There's no experimental there's no experimental way to verify, the Copenhagen versus the many worlds interpretation of quantum mechanics. So it becomes more philosophy than physics. So it's important that there could be a measurement that tell you that string theory was actually right. They could suddenly pop on our plate someday and we'd find them and we'd be very happy. But I'm not betting that that's going to happen. Yeah.
Well, returning to our thread, pun intended again, you have played an instrumental role in developing our understanding of Calabi-Yau shapes, which have come up a few times, and which I think also might help make sense of what these 6-dimensional spaces are like that we're appending to our more...
Wait, those are the Calabi-Yau manifolds. Those are the 6-dimensional spaces.
Right. I guess I meant they might help us make sense of how to visualize them. But maybe you don't think so. But I was going to say is there talking about the geometry, but is there a simple way of explaining the basics of your work here and the relevance that these shapes have to string theory?
Well, I can say something about them, but first of all, I think you can describe you can describe spaces by equations. So the simple example of that is if we have a plane labeled by X and Y, that all the points obeying X squared plus Y squared equals 1 lie on a circle. So that's one way of describing a circle. You start with just a flat chalkboard, and then you have an equation, X squared plus Y squared equals 1, and the points that obey that form a circle. So there's a map from equations of the right sort into spaces, in this case, the space being the circle. If we were in 3 dimensions, we could have X squared plus Y squared plus Z squared equals 1. That would be a sphere. Now, there are much more complicated equations, and you can have whole sets of equations, and that's a way of describing spaces. And that's a subject known as algebraic geometry. You describe spaces using algebra. And Calabi-Yau spaces, among all the possible, it's just a whole zoo of things you might try to describe. But I think it's fair to say that already in the 50s, Calabi realized that there might be and he made a conjecture, the Calabi conjecture, that there might be a space with some very special properties that you could get a nice solution of. And this is an example, of course, of interaction between mathematics and physics, that you might, there was a very special kind of complicated, knotty, tied up space that you might actually be able to solve Einstein equation on that space. And these spaces had a lot of beautiful mathematical properties. And it's fair to say that it was definitely one of the prime topics in mathematics in the 20th century, understanding the spaces. And he made this conjecture, which Yau proved in the early 70s. And then we discovered that the conditions which led the mathematicians to discover, mathematicians just like things that are beautiful. That's their only criterion. They don't worry about experiment. And they don't worry about describing nature. So amazingly and very gratifyingly, we found some consistency conditions from string theory that, after rewriting them and massaging them and putting them into the language of the mathematician, turned out to be exactly the conditions that Calabi had arrived on from a completely different point of view. And whose solutions to which had been proven by Yau. So you kind of know you're on the right track, or you feel that you're on the right track. It's like a signpost that you're on the right track when your work leads you somewhere to some territory that somebody else has been driven to from some other, possibly completely different point of view. And that happened many times with string theory. This was one example of it. And it happened a little bit later with Hawking's work. Things came together, and so But as far as visualizing what the spaces actually are, it's pretty hard to do. There is a Yao's hometown. I wanted to go with them to see it. I didn't quite make it. I might sometime I'll go see it. But Yao's hometown. He's a very, very famous. He's famous in the whole world, but he's very, very, very famous in China. And his hometown in Shenzhen, I think, has a statue 4 meters high of a Calabi-Yau space, of an artist's rendition of the Calabi-Yau space. So that's kind of the best that you could do. But I don't know what to do. They're complicated space with a lot of knobs and handles and different ways to get from A to Z, and different minimal surfaces, and a lot of beautiful a lot of very, very intricate structural properties, and yeah.
Well, maybe one way of making the Calabi-Yau spaces more tangible for us, even if we can't visualize them, is explaining their relationship to the particles in the standard model, and particularly they have a very neat relationship, as I understand it, to the 3 families of particles, the quarks, leptons, and bosons, that I think you played a role in discovering.
Right. Yeah, absolutely. So, okay, so you have to ask. I told you before that I talked about how the strings take on various disguises depending on exactly how they're vibrating, and vibrating, rotating, whatever they're doing. And in that discussion, strings, before you start compactifying on Calabi-Yau spaces, that discussion was really about just 10-dimensional flat space. No compactification. But now when you have a string on a Calabi-Yau space, there are a lot more things it can do. It can spread itself out. The string can kind of spread itself out and get in some kind of resonant cyclic orbit, where it have you seen those? I've never used this analogy before, but in airports now, there's some artist, I don't know his name, but they have these things where a ball starts at the top. These sculptures, you see them at airports and stuff. They're usually like, 20 feet by 10 feet. A ball start at the top, roll down a coaster. It may go around like this and hit a lever, bounce, and wind its way around down. Have you seen those things?
Like it's a Rube Goldberg type machine?
Like a Rube Goldberg type machine, yeah.
I haven't seen these.
You haven't seen these. Maybe they're out of fashion now. But there are many ways that things can move around, bounce off, different trajectories that they could have. Like imagine a string on a Calabi-Yau space. It can bounce off one corner and go to the third corner, twirl around a couple times, come back down, go to the fourth corner, and then if everything's arranged just right, it can have some special pattern that it'll just resonate and keep repeating. So the strings can do very interesting things when they're wandering around in a Calabi-Yau space. And they're related. The interesting things that they can do are related to the topology of the Calabi-Yau space. And topology we can think of as sort of the simplest example of a topology is like, a sphere. There's no handles on a sphere, but surface of a donut, it's like one handle. Then you can have a two-hole donut, so on. So you can have different topological surfaces. And so Calabi-Yau spaces have a lot of intricate, interrelated topology, which provides for strings resonating in a very coherent and cohesive way with the internal Calabi-Yau space. And all of this gets translated into structures that the mathematicians have spent the last century or two working out. It's very intricate. The fat textbooks on how this stuff works out. So we were able to take all that math and from it deduce the way that particles, the spectrum of particles, we needed that to understand whether string theory on a Calabi-Yau space had electrons and quarks and the right numbers of them and so on. And even more beautifully, the next question we wanted to ask is, okay, now from it would be a gross oversimplification to say that the number of species of quarks, numbers of flavors of quarks, is the number of knobs on the Calabi-Yau space. But it's some very complex version of that. Now, then the next question you want to ask is, well, how do these things bounce off each other? How do they interact? As a physicist would say, what is the coupling between the electron and the photon, or between the quark and the electron and the neutrino, or whatever? Now, this turns out, in the framework of string theory, quite beautifully, to be translated into another math question that the mathematicians had solved after a century or so of work. It wasn't a matter of just adding and subtracting. This has happened time and time again, now we come to expect it, that every time there's some question in string theory, mathematicians have already solved it, except that every once in a while, we come on a question that the mathematicians haven't solved. Then we go and talk to them and we say, hey, why haven't you guys solved this? And string theory suggests that the answer should be this. And then they'll go and they'll say, wow, that was a great question. Why didn't we think to ask that? And then they calculate for a while. And then every time this has happened, there's been agreement. And it's been stimulating both for the mathematicians and for the physicists. But string theory has had a huge impact on modern mathematics.